This is lecture 10F on spirals. There's several different kinds of spirals. We'll look at three of them here. The first is the Archimedean spiral. The spiral is given by this equation. In general, R equals some constant A times theta plus R naught. In these spirals, you're not going to see the sine, the cosine like you saw for those other curves, or like the roses and the circles. Here you're going to see R varying with theta, and that allows R, as theta increases, R increases. Or you could have the inverse relation in another spiral. You see a relationship between R and theta here. R naught is just the center. If R naught is 0, then it's centered right at the pole at 0, 0. The spiral will wind out from the center. Let's say it starts at the center. It winds out. The interesting thing about this Archimedean spiral is that when you look at the spiral arms, there's a constant difference from one arm to the next, a constant spacing between the arms. If you're looking at, you have to look on a line of constant theta, of course, because the spiral is always increasing here. And the spacing is A times 2 pi. The result of this is you can, as it says here, you can shrink and enlarge spirals, Archimedean spirals, so they all fit inside. They can fit on top of one another or into the other one. And here's a picture of an Archimedean spiral. This is just a graph of one. In this case, it's an Archimedean spiral with R equal to 10 theta. Right. It's going to start at R equals 0, theta equals 0, and spiral out. And if you look, you'll notice that the spacing between the arms is 2 pi times A. In this case, A is 10, and the spacing is 20 pi. That occurs between every arm of the spiral as it winds out. And so that's your Archimedean spiral. The second spiral is called a hyperbolic spiral. It's the inverse, in a sense, to the Archimedean spiral, in that it starts out at infinity and it winds in. Here's the polar equation. So R is inversely related to theta. This is an example from nature of a hyperbolic spiral. It's a pinwheel galaxy seen through the Hubble telescope, and you can actually fit this equation, R equals A over theta, to these various arms as they spiral in. Yep, messed that one up a little bit, but you get the idea that this, in fact, that makes it look worse. You can see, here's your spiral, here's your hyperbolic spiral over here, spiraling towards the center, and you can see the correspondence between that and this pinwheel galaxy. The third spiral is called logarithmic spiral, or the equiangular spiral, and this is commonly seen in nature. This is seen in various shells. It's seen in broccoli and patterns of sunflower seeds make on the head of the sunflower seed. And it has slightly different properties from the equiangular spiral of the Archimedean spiral. This is the polar equation for this logarithmic spiral, or equiangular spiral. R equals some constant B times e to the 8 theta. Now, it can spiral in or out. If A is greater than 0, it spirals out. It spirals in if A is less than 0. And if you notice, when theta is 0, R is equal to B. It starts at B with theta equal to 0. So it can start anywhere, either spiraling in or out, depending on the value of A. So I've done a graph here, and let me see if, I guess you can see it. It's probably better in the written lecture notes. So in this case, A is negative, and that creates a blue spiral spiraling in towards the center. And here is the other, the red one. A is positive at 0.1, and this spiral starts also at 1, R equal 1, theta of 0, but it spirals out. The one feature of this logarithmic spiral is that for fixed theta, for fixed angle, the arms always cross the angle, the line from the pole. They always cross at the same angle. Let's see if I can, let me go back and show you that. Here's an enlarged picture of that graph of the logarithmic spiral. And this property that we're talking about, well, first of all, note that the spacing between the arms is not constant, as it was with the Archimedean spiral. But the property of this spiral is that for constant angle, let's say theta equals 0 in this case. Try the pen again. Okay, so with theta equals 0, that looks like a little something. Theta equals 0, so we're going to look right here at theta equals 0. Then the angle that these arms make with the line theta equals 0 is going to be the same. This angle is the same as this angle. So if you drew an arbitrary, let me get a real line. So let's just put some line out here. Okay, fine. And then if you looked at the angle that these arms make with this line theta equal constant, all these are going to be the same. And we're going to prove that from the equation in a minute. So that's a property of this logarithmic spiral. So what we're looking at is the derivative of the curve. We want dy by dx. And for a parametric equation, dy by dx is the derivative of y with respect to the parameter divided by the derivative of x with respect to the parameter. In this case, the parameter, in polar coordinates in general, the parameter is theta. So we need dy by dx and dx by d theta. So we have to convert from polar coordinates into Cartesian coordinates. So in polar coordinates, x is r cosine theta, but we know what r is. Let's see. R is b times e to the a theta, because this is a logarithmic spiral. Also for y equals r sine theta. Again, we know what r is, and we just substitute that here. Now we have an expression for x and y, the Cartesian coordinates, and we can take the derivatives with respect to theta, and we get these two expressions here. Derivative of x with respect to theta, using the product rule, is b a e to the a theta times the cosine of theta minus b e to the a theta times the sine of theta. The derivative of y with respect to theta is similar. It's right here. Of course, you have the plus sign and the cosine, so the sine and cosines are changed, and there's one sign difference. Now we're going to take the ratio of those two expressions. So we take the ratio. We find, of course, that it depends only on angle. We can simplify this, and we end up with a sine theta plus cosine theta divided by a cosine theta minus sine theta. So at each turn of the arm, the angle, it depends not only on angle, but in the simplified form here, right here, it depends only on the sine and the cosine of the angle. So at every turn of the arm, the angle advances by 2 pi. But sine and cosine do not change because they are 2 pi periodic. So the derivative for every complete turn of the cycle, no matter where you start, every 2 pi, the derivative is the same because the sine, cosine, and cosine are the same because of their periodicity. So that's a proof of this equal angular property of the logarithmic spiral. And here is a logarithmic spiral in a storm over Iceland, I believe. This is from what's on several websites, but it's a very good picture of an equal angular spiral. In fact, if you look at it, you could draw your line of constant theta, and notice the angle is constant, and as the arms cross this line, theta equal constant. And here's a summary of these 3 spirals. There are other spirals, but these are the 3 main ones. So here's your Archimedean spiral. R equals a theta. R is directly proportional to theta, right? And we can add a plus r naught here to get it to start at some particular value, some particular radius. It's going to spiral out. There's going to be equal spacing between the arms. Right? This is the hyperbolic spiral. In this, r is inversely proportional to theta. This spiral spirals in from infinity. The logarithmic or equal angular spiral has this exponential form. You'd say it should be exponential spiral instead of logarithmic, but it's called logarithmic. R equals some constant b times e to the a theta. Now in this spiral, it will go out. It will spiral out if a is greater than 0, and spiral in if a is less than 0. And it starts at r equal b and theta equals 0. And this is a spiral at which the arms make constant angle with any line theta equal constant.